Hello students! Quadratic functions. Now in everyday life, objects follow curved paths, such as a ball flying through the air. Mathematical modeling allows us to represent and analyze such phenomena. For example, if a ball is kicked through the air, how high does the ball go? What function models the path of the ball? In this unit, we will develop the tools to answer such questions. And we'll begin by using transformations to graph the following functions. Y equals x squared, 0, 0 is a point on this, 1, 1 is a point, and so is 2, 4. Negative 1, 1 and negative 2, 4 are also points. And we have the graph of a parabola. Now when you do negative 4x squared, well the negative will do the reflection and the 4 will do a vertical stretching by a factor of 4. And you could just plug in some coordinates here. Plug in 0, you still get 0 back for y, so that point doesn't move. But when you plug in 1, you get negative 4 for y. And when you plug in negative 1, don't forget to square the negative and the 1 both. So when you square negative 1, you get positive 1, and then times negative 4, you still get negative 4 down here. And you have a much more narrow parabola. It's been vertically stretched, and it's been reflected. Next, transformation. Here, to go from this to this, we have replaced the x's with x plus 1s. That is the transformation that does a shift left 1 unit. And then finally, the last phase, this plus 9 here at the end, that's the vertical shift up 9. This point right here, negative 1, 0, is now up at negative 1, 9. And the point 0, negative 4, shift that up 9 units, will be at 0, 5. And we have a parabola that looks something like this. Now quadratic functions are all the possible transformations of x squared. And there are 3 primary forms for expressing the rule of a quadratic function. First one is the standard form. This is similar to the form that we saw right here. Notice we have a number in front of the parentheses. We have x plus or minus a number inside the parentheses with then the square. And then we have adding a number at the end. This is your standard form. Some number in front of the parentheses. X minus h is the standard form, we'll say, and then add k. Now, a could be negative or positive, h could be negative or positive. And when you replace h with like negative 2, then this would look like x plus 2 inside here. So the standard form isn't trying to say this always has to be subtraction here. Same thing for k. K could be positive or negative. If k is a negative 9, then you would see a subtraction of 9 here at the end. General form. Now, if you take standard form and expand it and regather terms, you'll get general form. Ax squared plus bx plus c. And then there's also a factored form. In this general form right here, the b and the c could also be negative, as could be the a. Some of these could also be 0. The only one we don't want to be 0, though, is a. Because if a is 0, then this term is not present, and this is no longer a quadratic function. So in none of these cases do we want a to be 0. And they're all the same a, by the way. That's why I'm using the same letter. The a is also sometimes called the leading coefficient, because it's the number in front of the highest power term when you're in general form. Over here, I'm using R1 and R2. The R stands for root. Now, you're going to want to know how to go back and forth between all of these forms. We're going to start with quadratic function that's in standard form, the same one we just graphed on the last slide. And we're going to practice getting to general form and then to factored form. And then we're going to practice going backwards. Let's begin by going to general form. You do the exponent first. You leave the minus 4 out and you do the foiling first, outsides, insides, last. So x times x is x squared, plus x is going to be plus 2x, and then plus 1, then plus 9. Distribute the negative 4 next, and then combine any similar terms. The negative 4 and the 9 can be combined. And just like that, we have obtained general form. Put that in a box. Standard form in a box as well. And the process that we did here was FOIL and then combine. Or the single word of doing all that stuff is just we expanded. To go backwards will be a little bit trickier. Well, I'll show you those steps in a moment. But let's keep moving forward to factored form. Well, first of all, look to all 3 terms. If you see anything that's common, any number that divides into all 3 of the coefficients here, then you want to factor that out. Also, I recommend if the leading coefficient is negative, then begin by factoring out a minus sign. So that leaves negative and then parentheses 4x squared plus 8x minus 5. Now I want to try to factor this. There are several ways this might factor. There's the guess and check method, which is what I typically do. You can think 4x and x as one way to split up 4x squared. Minus 5, there aren't that many options. I could put minus 5 here and positive 1 here, and if you FOIL this, it won't work. So maybe I should make the 5 positive and then 1 negative, and this still won't work. So then I think, okay, well maybe I should switch the 5 and 1 around, make 5 positive, the 1 negative. This won't work when you FOIL it. So when you turns out none of the options will work when you split 4x squared as 4x and x. So another option, of course, is to split it up as 2x and 2x. And now it turns out if I put a plus 5 on one of these and a minus 1 on the other, and then do the FOIL process, let's just check real fast. 2x times 2x is 4x squared, check. Then we have plus 10x minus 2x, that's going to be plus 8x, and then minus 5. So this works out. And you could technically stop here and call this factored form, but it doesn't exactly match this one here because the factored form that's written here has the leading coefficient in the front, and then notice the coefficients of the x's in the parentheses. These x's here have 1s in front. That's not the case down here. So if you wanted to take this further, you could factor out a 2 from each of these factors and combine the 2's into a minus 4 in the front. So you could go up to this point, negative 4, factor a 2 out of here and here. So it leaves an x and a minus 1/2. Factor a 2 out of both of those, it leaves an x and a plus 5/2. And this is the factored form that is referred to up here. So we have the a, the leading coefficient is in the front, and you have x minus r1 and x minus r2. Now one of these is addition. That just means that r2 is negative 5/2. And this process here, of course, is called factoring. Now to go backwards is rather straightforward. To go from factored form back up to general form, you also expand. And to do that, you have to be careful about how you expand this. When you have this minus 4, you could break it up into 2 and 2, distribute one of the 2's through here and distribute the other 2 through there so that it now looks like this. And then with this negative sign, I would just leave that out. I would FOIL that next and go here, and then I would distribute the negative across the parentheses last. But there's lots of options here. You could take the minus 4 and distribute it only through one of these. The minus 4 does not distribute here and distribute here because between these here is multiplication. Right? When you have 3 things being multiplied, 2 times 5 times 3, the 2 does not distribute in this case. You pick one or the other to multiply the 2 by, and then you multiply that by the remaining factor. But if you want to distribute the 4 through here first and get a result, and then FOIL that result with this, and that's another way that will take you back. Now the trickier one is to go from general form back to standard form. Alright, now to go from general form to standard form, we have to do a process called complete the square. We begin with the general form, negative 4x squared minus 8x plus 5. We factor the leading coefficient, but out of the first 2 terms only. So factor a negative 4 out of only the first 2 terms. That becomes a plus of 2x and then plus a 5. Now what you want to do is you want to create a little bit of space. You want to do what's called completing the square, and you want to figure out what number is needed right here so that this factors into a perfect square. Now just a quick review of what a perfect square, what to expect. Let's say you had x minus 3 times x minus 3. What I mean by perfect square is that you have a square on the binomial, on the 2 terms. Or in other words, it's something multiplied with itself. And if we had x minus 3 times x minus 3 and you FOILed this, you would get x squared minus 6x plus 9. Now look at the connections. If you didn't know the 9 and you're trying to figure it out so that this would factor into a perfect square, you can determine what number should be there in that place by looking at the coefficient of the x. Right, this minus 6 came from doing a minus 3 and another minus 3 combined together. So if you take the minus 6 and cut it in half, that will reveal what numbers are here and here. And then if you square that number, it tells you what needs to be right there. So in order to figure out what number we need to put right there, we take the 2, that 2 right there, and then we divide it by 2, and then square the result. A lot of 2's there, and that result will give you a 1. This is the number that you need to add and subtract. Make sure if you just add it, then you've changed things. But if you add it and then remove it, then you haven't changed your function. So you need to add and subtract it. It's like adding 0 to your function. Okay, once you determine that, then this needs to come out of the parentheses, but in order to do that, you're going to have to distribute this negative 4 to that negative 1. But leave the negative 4 factored out of the first 3 terms. But remove the negative 1 from the parentheses by multiplying the negative 4 to it, becomes a positive 4. And then the plus 5, of course, is still there. These 3 here form a perfect square. When you factor it, it factors into x plus 1 times itself, with a negative 4 in front, and then the positive 4 and positive 5 there combined to be positive 9. Just like that, we've been able to reconstruct the standard form. You have to be comfortable moving back and forth pretty fluidly between all of these forms. They all have different uses when you're analyzing the quadratic function. Quadratic functions produce the shape of a parabola when graphed. If the independent variable is the horizontal axis, then the parabola will either open upwards or downwards. Now, it's possible to have functions of y and your parabolas are sideways like this, but if you're talking about a function of x and x is the horizontal axis, then when you graph a function of x that's quadratic, you will get a parabola opening up or down. In each diagram below, identify the intercepts, vertex, axis of symmetry, and whether the leading coefficient is positive or negative. Also give the domain and range and the intervals where the function is increasing and decreasing. So lots of stuff here to do for each image. So identify the intercepts. Let's go y-intercept first. So 0, 3 is the y-intercept in this image, but 0, negative 2 is the y-intercept in this one, the location of where the parabola crosses the y-axis. Every parabola will have a y-intercept. The x-intercepts are the other kinds of intercepts. This one appears to have two x-intercepts. We have negative 3, 0 and negative 1, 0. This other one has no x-intercepts. Not every parabola has to cross the x-axis. In fact, it's possible for a parabola to have only one x-intercept. Right? Think about what that might look like. The vertex is either the lowest point or the highest point, depending which way it's opening. So in this case, the vertex is the lowest point, sometimes called the minimum point of the parabola, and it's located at negative 2, negative 1. And in this image here, it looks like it's at 2, negative 1. Axis of symmetry. All parabolas are symmetric around some vertical line, and that vertical line is called the axis of symmetry. And it's always the line that goes through the vertex. And the equation is always x equals, and then the x-coordinate of the vertex. So x equals negative 2 in this case, and in this case over here, the axis of symmetry is x equals 2. Next, whether the leading coefficient is positive or negative. So we'll use A to represent the leading coefficient. If the parabola is opening upwards, then a reflection has not occurred around the x-axis. So in this case here, we know that A would be positive. And in this case here, there was a reflection, so we knew the leading coefficient had to be negative. And next, also give the domain and range of the intervals where the function is increasing and decreasing. The domain is always going to be all real numbers, and the range will be limited for every parabola. The lowest point in this one is at the vertex, and negative 1 is the lowest possible y-coordinate, and every y-coordinate above is possible, right? Because we do assume that the parabola continues on both branches. Same with this one over here, continues downwards with both branches. The domain of this one is also all real numbers. All parabolas have domain real numbers, unless you crop them, unless you impose a restricted domain for whatever reason. And the range on this one is the lowest is negative infinity. I notice some people sometimes like to put the negative infinity here. They think high to low. So they'll put the negative 1 here, it goes negative 1 to negative infinity. But you should always write your intervals from lowest to greatest. So negative infinity is the lowest, and the greatest is negative 1 bracket. And then finally, where's the function increase and decrease? We can say the function increases on and then give an interval, and the graph is going up for this branch right here. So any x more than negative 2, and you just have to say where the x's are, and give an open interval from negative 1 to infinity. And if decreases, it's decreasing on this branch. When you're answering increasing, decreasing questions, you always imagine going this way with your x-coordinates. So as x increases, what's y doing? So in this case, this side, it's going down. And so it's decreasing on the interval from negative infinity up to negative 1. On this one here, this function's increasing on this portion right here. And I don't know why I wrote negative 1 over here. These should be negative 2's. It's the x-coordinates that you're focused on. So we're increasing on negative infinity to 2, given open interval, and the function's decreasing after the vertex, so 2 to infinity. Use technology to graph several examples of each form of the quadratic function, then do your best to fill in the table. Feel free to leave any entry blank for the moment, because we will fill in the rest of the table by the end of this lesson. Okay, so I'm going to just go to Desmos and type in y equals and exactly what you see right there. Add sliders for all three, so say all, and then we have a parabola. As you move A around, notice a few things. It appears like A is definitely affecting the narrowness or wideness of the parabola as well as which way it's opening. So if I make h and k both be 0, notice we just have a parabola at the origin, just like the parent. If h goes positive, then this graph shifts right, because your standard form is x minus h. And remember, x minus a number, like x minus 3 in those parentheses, would mean shift right 3. When h is positive, it goes right. When h is negative, it goes left. And k goes in the direction we expect. So when it's plus a positive number, it meant it will shift it up. If it's plus a negative number, it meant it will shift it down. So the h and the k actually reveal the vertex. Okay, so back to our table, the vertex will just simply be hk. The axis of symmetry will be x equals h. It's always the x-coordinate of the vertex. The x-intercepts aren't obvious, but if we wanted to find them by hand, we set the rule of the function equal to 0, and then we solve for x. But the general rule for finding x-intercepts is, remember, there is an implied y here. You change the y to a 0, and you solve this equation. I'm going to subtract the k and divide by the a, so we have x minus h quantity squared is equal to negative k over a, and this could be positive or negative. It depends what a and k are. take the square root first, so you get plus or minus the square root of negative k over a. And remember, negative k over a isn't necessarily negative. If it is negative, then we don't have x-intercepts. If it's not negative, and then we can complete this. And then you add h to that, and you get two different possible x-intercepts. The only way that this will give you only one x-intercept is if k is 0. In other words, if you don't have a vertical shift involved, all you have is a left-right shift, you can see why your vertex would stay on the x-axis, giving you only one x-intercept. Now, I don't expect you to memorize this formula. I do expect you to memorize this, though. When you want to find an x-intercept, you solve y equals 0. Now, if you want to do a y-intercept, then you simply plug 0 into the function, right? I could call this f of x equals, and so just plug 0 into the function. If you plug 0 into this, you get negative h. Square that goes positive h squared times a, and then add k. So you wind up getting ah squared plus k. Now, again, you don't need to memorize this formula, but you do need to memorize and understand how to find a y-intercept by letting x be 0. Okay, let's go to the general form next. Now again, when you mess around with a, notice b and c are currently 1. It's kind of hard to predict where the vertex is going to be. But we certainly get it, the graph is opening up when a is positive, and the larger a gets, the more narrow the parabola is. Same thing's true in the other direction. When a is negative, we have a reflection involved, opening down, and the more negative it becomes, the more narrow the graph becomes. Messing with b, we've got this vertex going around. If you park a and b at a certain number and then only toy with c, we get vertical shifts. It does seem pretty clear that at least we can easily spot the y-intercept from the ABC. The c is going to be the y-intercept. I'm not sure I can easily see what the vertex is going to be yet, so therefore I don't know the axis of symmetry. This was hard to do right now, but the easy thing to spot here is the y-intercept, because if you let x be 0, plug in 0, those goes away, and you always just get c back. So f of 0 is just c. So that's something you can just spot. There's the y-intercept, but only in general form. Be careful. Some students look at this k and think that's the y-intercept. Not true. ah squared plus k will wind up being the y-intercept. If I want to solve for y equals 0, I'd have to say 0 equals ax squared plus bx plus c. And you could use the quadratic formula, which we'll review on another slide. That's one way you could get the x-intercepts. And the vertex, we're going to leave those blank for now. We'll see if we can come back to that. Let's now explore with technology this factored form. Okay, again, if you toy with a, same phenomenon that we see. And both r's are currently set to 1. If I change one of them, look at the two intercepts. They are the two r's, negative 5 and positive 1. Or the r's reveal the x-intercepts. When they're the same, they're both negative 2. Notice that we have just one x-intercept, and that's when the vertex is on the x-axis. But otherwise, if the r's are different, we do get two different x-intercepts. I should mention also that not every quadratic has a factored form where the r's are real numbers. Later in this class, we will talk about the possibility of factoring a quadratic where the r's are complex numbers, where they involve the imaginary number I, but that's for a later topic. So right now we're going to say that we only are interested in factored forms where the r's are real numbers, and if I make that insistence, then not every quadratic can be factored. So every quadratic will have both of these forms, but not every quadratic has a factored form. So the thing that became obvious, though, is that the x-intercepts are the two r's. So when you do the x-intercepts and you're trying to solve for y equals 0, you wind up solving this equation. Now the a becomes inconsequential. Right? You could divide both sides by a and just make it go away, because 0 divided by a will still be 0. And then when you set the two other factors equal to 0, you use the zero product property. If something times something else equals 0, then either this is 0 or this is 0. That's the only way that that can happen. So we solve x minus r1 is equal to 0, and we solve x minus r2 is equal to 0, and that gives us that the two x-intercepts are r1 and r2. The y-intercept is always found the same way. You let x be 0, and up here when you do that, when you change these two x's to 0, you get negative r1 times negative r2. That gives you r1, r2, and then times a. So plug 0 into the function, and you wind up getting a times the product of the intercepts. Again, you don't need to memorize this. It's an interesting observation, but what you do need to know is that you should let x be 0 when you're trying to find a y-intercept. And what you should know up here is that when you want to find x-intercepts, you let y be 0 and solve for x. How about the vertex? Because of symmetry, let me park r at negative 3 and at positive 1. Identify where the vertex is. I'm going to highlight these 3 points. So if you know the two x-intercepts, doesn't it seem reasonable that the axis of symmetry should be halfway in between? So halfway between negative 3 and 1, they're 4 units apart. Go 2 units from either one. Start at negative 3 and go 2 units right. Takes you to negative 1. So x equals negative 1, right? That is the axis of symmetry. Therefore, you would expect the vertex to be on it. So this is interesting. If you know that what the two x-intercepts of a parabola are, you can find their middle x-coordinate and then plug that into the function to get the corresponding y-coordinate, and you've got the vertex. Now, one way to find the middle of two numbers, you add them together and divide by 2. You average them. To find the vertex, if I'm in factored form, I could get the x-coordinate by averaging the two x-intercepts. And then once you have that, you plug that into the function, and you get the y-coordinate of the vertex. And of course, the axis of symmetry. Once you have something for the x-coordinate of the vertex, the axis of symmetry is simply x equals that same x-coordinate. So we're going to leave these 2 question marks here unfilled in for the time being. We'll come back to this table. We're going to use factoring to find the x-intercepts of each quadratic function. Notice all 3 of these are given in general form. Then use the x-intercepts to find the vertex, next find the y-intercept, and then graph the function by hand. Okay, here we go. Now this one we've already factored. Notice this is our same f of x function. I factored it by taking the negative out, then I factored the rest, and if you recall, this was our factoring. Once you change the function to 0 to find the x-intercepts, is just set these factors equal to 0 separately and just solve for x. And you're going to wind up getting the 2 roots. They're called roots, by the way. That's why the r is being used. When you're talking about a value of x that when you plug it in that produces 0 as a result, we call that value of x a root. Negative 5 halves. These are the 2 x-intercepts. Once you know the x-intercepts, let's go to the vertex. We average them. So we're going to do 1/2 of, and then add 1/2 and negative 5 halves. So 1/2 plus negative 5 halves is negative 4 halves is negative 2. Then do half of that, we get negative 1. The y-coordinate of the vertex is we take the negative 1 and plug it into the function. So right here we do plug in negative 1. Negative 1 squared is positive 1 times negative 4. So we just get negative 4 to start. Negative 1 times negative 8 is positive 8. And then positive 5. And this gives me 9. And then the last thing we're asked to find here is the y-intercept. And that's where you just plug 0 in for x, and you're going to get the c, the 5, right? When you're in general form, it's always that number there that gives you the y-intercept. Now we're ready to plot. So I don't have the axes here yet, so let's put them here. I do see I have to go up to negative 1, 9, so I'm going to put my x-axis very low. Let's start with the vertex, negative 1, up 9. 0, 5 was the y-intercept, and then the 2 x-intercepts, one was at 1/2, which is right here, and the other is at negative 5 halves, which is negative 2.5, right there. And here is our graph. Notice this is the exact same graph as what we did here in the original. What I have circled here is in standard form, and we were just working with the general form instead. Okay, let's go over to the next one. This is a general form that has no c, which means it's very easy to factor. You just have to take out, I see a 2 can factor out, but always an x can be factored out when there's no c. Change this to 0 and solve for x. Set the factors equal to 0 separately. The 2 does not affect anything because it can divide away, but if this x is a 0, then so is the y-coordinate. And the other answer is if x is negative 3. So here's your 2 x-intercepts. Now let's go for the vertex. The x-coordinate will be 1/2 and average these 2 x-intercepts. So 0 plus negative 3, or 0 minus 3. So we get negative 3 halves. The y-coordinate of the vertex is always found by plugging negative 3 halves into the function. So we're going to have to square negative 3 halves. That's going to be 9/4 times 2 will be 9 halves. And then minus 3 halves times 6 is negative 18 halves, and we get negative 9 halves. And then the y-intercept is next. Plug in 0, and you get 0 back. Notice there is no c, right? When there's no c here, then your y-intercept is 0. All right, so I'm looking at our points here and trying to determine where I need to put my axes so we can see everything of interest. Our x-intercepts are 0 and negative 3. Our vertex was negative 3 halves, which is negative 1.5, and negative 9 halves, which is negative 4.5. And the y-intercept was also 0. Yeah, whenever the x-intercept is 0, then so is the y-intercept. And this would be our parabola opening up. Okay, and then let's do one more. I notice a 3 can factor out of everything, so I'll do that first. And here we have to do some reverse foiling, x and x. I think -1 and -1 should do it. So when you set this equal to 0, you only get 1 x-intercept, 1. We've effectively just put this one without meaning to. We just put it into standard form with a k being 0. This is standard form as well. Notice if you started as x squared as the parent, there's a shift right 1 and a stretching by 3. But anyway, if I set this equal to 0 and solve, I get x equals 1, which is not surprising because that's where the vertex is now. When there's only one x-intercept, then that is going to be where your vertex is. So we know that our vertex also is going to have x being 1, and the y-coordinate will be f of 1, which should be 0. If you plug 1 into this, you'll get 0. But it makes more sense when you plug 1 into this, you get 0. And then finally, we want to do the y-intercept. So we do f of 0, plug 0 in for x up here. We're going to get that 3, the c. 1, 0 is the vertex and the only x-intercept. 0, 3 is the y-intercept. I know that there's going to be a point there as well. There has to be. by symmetry. That's easy to check, right? If you plug in 2 in for x, and you get 3 back for y. Okay, there we go. Here's how you can graph pretty quickly by doing the factoring, getting the x-intercepts first, then the vertex next, and then the y-intercept and graph it. Now, this will run into a snag, of course, if you cannot factor. You can't find the x-intercepts very easily. So now let's go and review the quadratic formula. It's something you need to memorize if you don't have it memorized already. If ax squared plus bx plus c is equal to 0, and a is not 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac, all in the radical, all over 2a. If you split the 2a up, you could write it this way. Negative b over 2a, and then plus and minus the radical, b squared minus 4ac, or that is over its own 2a. You might recall that the inside of the radical is called the discriminant. If the discriminant is positive, then you're able to do these radicals. If the discriminant is 0, then this whole part just goes away, and you get one answer out of this. And if the discriminant is negative, then you have imaginary numbers involved, and we would say that there's no real solution. In other words, this would not have any x-intercepts. And the quadratic formula is very helpful when it's not obvious how to factor, or maybe you can't even factor the quadratic. So let's just use the quadratic formula to find the x-intercepts of each quadratic function, then generalize our findings based off the discriminant. Okay, in this case, the a is the coefficient of the x squared, so a will be negative 1. The b is the coefficient of x, so b will be positive 2. And the c is the constant, so c will be positive 4. Now we simply apply the quadratic formula, and we get x is equal to negative b, so that's the opposite of b, plus or minus the square root of b squared minus 4 times a times c, and all of this will be over twice the value of a. Simplifying, we get negative 2 plus or minus the square root of, this will be 4 minus negative 16, so plus 16, all over negative 2. Now I'm going to split the negative 2 in the denominator up, so we have negative 2 over negative 2, plus or minus the square root of 20 over negative 2. Now this negative can be brought to the front of the fraction combining with these operations, changing their signs, but since we already have plus and minus as two different options, when I negate those, I still have plus and minus. Negative 2 over negative 2 is positive 1. We're still going to have plus or minus, and we have radical 2, and I can simply say over positive 2 now. Radical 20. 20 is 4 times 5, and 4 is a perfect square, so I can radical the 4 and radical the 5 separately, and the square root of 4 is 2. So we can write this as 1 plus or minus 2 radical 5 all over 2, and then the 2's can cancel, and so we just get 1 plus or minus radical 5. These are your two x-intercepts. They are centered at x is equal to 1. To find one x-intercept, we go to the right, radical 5. To find the other x-intercept, we go from 1 to the left, radical 5. Thus, 1 is the midpoint of the two x-intercepts. So this would be the axis of symmetry for this parabola. The leading coefficient was negative, so this would be an upside-down parabola, something like this. And observe how we found this 1 in the first place. It was in this position, right here, right here. It came from doing this part, which was really the negative b over the 2a, by doing this part of the quadratic formula. And then when the radical did exist, when it was a radical of a positive, we started here and we went plus and minus this exact same amount left and right. So this tells us that this should be the center of the two x-intercepts. In other words, it's the x-coordinate of the vertex. You can say that the x-coordinate of the vertex will be the negative b over 2a. This is the beginning of the quadratic formula, but without the plus-minus radical part. That's convenient. And then the y-coordinate will be found by plugging whatever that is into the function. And now we know the axis of symmetry will be x equals negative b over 2a. There we go. Now we have a strategy for finding the vertex, the axis of symmetry, and the x and y intercepts, no matter which form you're in. So if you're presented this form, then you can do all of these by going with this route. If you start in this form, you can do all of these by going these routes, etc. Or you can jump around forms too. Like if you're given this form right here, then you can find the x-intercepts only. But then you can expand it and put it in this form, and then you can go for the vertex next using that. Lots of ways to do this. Next one, we have a is equal to 2, b is equal to negative 3, and c is also equal to 2. So the quadratic formula will give us x equals negative b, so that's going to be 3 plus or minus the square root of. B squared is negative 3 squared. Make sure you don't say negative 9 here, because you want to square the negative and the 3. So b squared is 9. Minus 4ac. A and c are all positive. 4 times 2 times 2 is going to give me 16, so minus 16 all over 2a. Now, as soon as we see that we have a negative inside that radical, and I see that now, 3 plus or minus the radical negative 7 over 4, and we say these are not real solutions because you can't do square root of a negative. So we say there's no x-intercepts. This is a case where when you graph this particular parabola, you're going to see that it does not touch the x-axis at all. Okay, and so when the discriminant is negative, it means we don't have any x-intercepts. In other words, if the discriminant is positive, we have 2 x-intercepts, which we saw in the first case. Now, as you can imagine, this next case is going to be, and notice this is h. H is, I'm using the same letter to refer because this one was also h. So this one is resurfacing. Let's do x equals negative b, so 6 plus or minus the square root of b squared, which is 36, minus 4ac. Well, 4 times 3 is 12 times the c, that's times another 3, that's also 36. All over 2a, 2a is 6. So in the end, this winds up just giving you one answer, just one. This tells us that the vertex is there as well. And that's because, right, when you actually factor h, it wound up looking like this. And when you think transformations, this is just x squared stretched and then shifted right 1. So of course the vertex is at 1, 0. If I were to back up and do the vertex strategy of doing negative b over 2a, let's see if we can confirm some of these answers. Let's just do the negative b over 2a, and the negative b is the negative 8 there, and the 2a is 2 times negative 4. Negative b over 2a gives me positive 8 over negative 8, and I get negative 1. Notice that's the same thing I got by averaging the x-coordinates of the x-intercepts. In this case here, we have negative b over 2a. Negative b is going to be negative 6. Doubling a is 4, so I get, simplify that, negative 3/2. Same thing I got by averaging the x-intercepts. And this last case here, if I do negative b over 2a is 6, over 2a is 6, we get 1 is the x-coordinate of the vertex. Find the quadratic function with vertex 1, negative 2, which passes through the point negative 3, negative 4, which is way over here. Then find the y-intercept, use symmetry to find 2 more points, then graph the parabola by hand. Okay, so knowing that the vertex is at 1, negative 2, the starting place for this is going to be standard form. In each case, if you start with standard form, you're going to have to figure out what a, h, and k are to complete your parabola. If you start in general form, you have to figure out what a, b, and c are to complete your parabola. And if you start in factored form, you have to find out what a, r1, and r2 are to complete your parabola. So in either case, you need to find 3 unknowns. But if you know the vertex, this is the way to go because you know the h and the k automatically. So all you have to do now is figure out a. Knowing the vertex means start with standard form. So let's go to standard form. We have f of x equals a times x minus h being squared plus k. And the vertex is 1, 2, so that means that the 1 is the h and the negative 2 is the k. So we can rewrite this now as f of x equals a times h is positive 1, so we do x minus 1. That meant we shifted right 1, and the k is negative 2, so we can just write minus 2. So I see a shift right 1 and a shift down 2. That's why the vertex is where it's at. And now all we have to do is figure out what a is so that we pass through our point. If I plug in negative 3 for x, I should get negative 4 for y. So we set the output to negative 4. At the same time, I change the input to negative 3. And then this leaves an equation that we just have to solve for a. So I'm going to add 2 to both sides. So we have negative 2 is equal to a. And negative 3 minus 1 is negative 4. And square that is 16. And then divide by 16. And simplify, we get negative 1/8 is a. So our function is negative 1/8 x minus 1 squared minus 2. Next it said find the y-intercept. Let's just plug 0 in next. So we get negative 1/8 times 0 minus 1 is negative 1 squared. That's 1. When I multiply with negative 1/8, nothing changes, but then minus 2. Negative 2 is negative 16/8, so negative 17/8, which is really just negative 2 1/8. It's negative 2 and go down another 1/8. So it's not very far below negative 2. It's right there. Okay, so there's the y-intercept. Use symmetry to find 2 more points. Okay, so if I went from the vertex left 1 and then down 1/8, then do the same thing, right 1 and down 1/8. And you should have a mirror image right here. Same y-coordinate as the y-intercept, but the x-coordinate's 2. And then from vertex to the other point, this was left 4, down 2. Do the same thing, right 4, down 2. It should take you to a mirror image point right there. And now we're ready to graph our parabola. And this wraps up the lesson on quadratic functions.